Hey there, it's Shannon Myers, and today we'll be looking at disproofs and algebraic proofs. So recall that to show a universal statement is false, what do we need to provide? Beautiful, we just need to find a counterexample. So in this first one, we need to find a counterexample to show that the statement for all sets A, B, and C, if B intersects C is a subset of A, then A minus B, that quantity intersect quantity A minus C equals the empty set. Okay, the trick to remember here is that there's one set that is a subset of every single set. Do you remember what that is? Beautiful. The null set or empty set is a subset of every single set. So if we had it where B intersects C was the empty set, you would still have that as a subset of the set A, but then it would be easy to find excluded elements for those set differences, the intersection of the set differences, to be something other than the empty set. So let's do it. Let's say we had, I don't know, we'll be so original. Let's say that the set A is 1, 2, 3. And suppose that the set B was 1. And let's say that the set C was 3. All right, so let's take a look at what we have going on. So B intersects C is going to be the empty set, which is a subset of the set A. And we would have A minus B are, what is that? Do you guys remember? Remember, it's the intersection of A and not B, right? So here, we don't want anything that's in the set B to be represented, but the things that are in set A should be represented. So this would then just be, beautiful, 2 and 3. And then A minus C would be, perfect, 1 and 2. And so now if I look at the intersection of these two sets, right, A and not B intersect A and not C, right, if I read it a little differently with the equivalence, what's that going to equal to? Perfect. They both have the element of 2 in there. And so that would be the set that contains the element 2. And that means it's not equal to the empty set. It's not empty. So here, let's look at a picture of what that would look like if we drew a little Venn diagram. Basically, we've got, this set A that has all those 3 elements, 1, 2, and 3. We have a set B and we have a set C. So remember that the difference between A and B, so everything that was in A but not in B, remember, was perfect, 2 and 3. And then everything that was in A and not in C was 1 and 2. So the way that these would look are 2 would be in A alone, right? Because it's not in B and it's not in C. And then we would have 3 would be in the intersection of A and B, because it still would have to be in A, right? Because of what we've set up here. And then 1 would be in the intersection of A and C. Cool, cool. So this is our counterexample here. All right, so theorem 6.3.1 says that for all integers n greater than or equal to 0, if a set X has n elements, then the power set of X that's a capital X, has 2 to the n elements. So if you recall, the power set of some set X is a set of all subsets of X. So let's look at this proof, and this proof ends up being a proof by mathematical induction. Okay, so here we go. We have this property, right? So we'll let the property P at n be the sentence any set with n elements has 2 to the n subsets. Okay, so just to be clear, let's identify that n is, or let n be a non-negative integer and so what do we do with when we're doing a proof by mathematical induction? Remember? Beautiful. We have a basis step and then an inductive step. Now remember, for our basis step, what are we checking? We want to check good. P at 0 because n can start at 0. So for n equals 0, if some set X has 0 elements, then it's empty, right? And the power set of X then would only have one subset, right? Which would be itself, which would be the empty set, right? So let's write that in. Okay, so that's the first part of it. If a set has no elements, in other words, it's empty, its only subset is the empty set. And how many subsets is that? Good, 1. Okay, now if I evaluate, P at 0, what's that really saying? Well, if I plug in a 0 where there's an n in my sentence, any set with 0 elements has 2 to the 0 subsets, 1, and that's what I had gotten in the step before, or the sentence before. So we're all good. Okay, what's next? Beautiful, the inductive step. Okay, for the inductive step, we'll put, our sentence in terms of K, and then we're going to be looking at the property evaluated at K plus 1. Okay, so let's identify everything. Why don't we let K be a non-negative integer and we're going to let the property P at K be the sentence any set with K elements has 2 to the K subsets. All right, so what are we checking again? Good, we need to check our property at K plus 1. So this one will be a little bit more complicated, but not too bad. What we need to do is we need to identify, some element that belongs to the set X. And then we're going to use the set difference property along with union to get this proof to fall out here. So why don't we also let X be a set with K plus 1 elements. Since K plus 1 is greater than or equal to 1, because remember K is greater than or equal to 0, there needs to exist, call it Y, an element Y that belongs to X. All right, so we know that X is not going to be empty. Now, any subset of X either has to have Y or not have Y. All right, so any subset of X either contains Y as an element or does not contain Y as an element. I guess that's a little redundant, but hopefully you can forgive me. So now let's think about this. Well, any subset of X that doesn't have Y is going to be the difference between X and the set which contains just Y. Okay? And then, now why don't we let A be a subset of the difference between X and the set which contains that element Y. A can be matched up with a subset B we'll call it a set B, which is equal to A union Y, that's set Y, So it's the set of A union the set Y, which is a subset of X. And of course, this contains Y. So there are as many subsets of X as there are subsets of the difference of X and the set Y. Well, okay. But don't we know something about, in our inductive set, don't we know this? Here we identified P of K to be the sentence, any set with K elements has 2 to the K subsets, right? So if we kind of bring that into play, what do we know? We know that the difference between X and the set of the element Y is equal to 2 to the K. Thus, the number of subsets of X is twice that. So 2 times 2 to the K, which is 2 to the K plus 1. And we've shown what we needed to show. Cool, cool? All right. So let's take a look at these examples. So we want to prove each statement that we think is true, and we want to provide a counter example for each statement that we think is false. So let's check them out. For all sets A and B, if A is a subset of B, then A intersect B complement is the empty set. Well, I think this is true, right? Because if A is a subset of B, what does that mean? It means that every single element that is in A is also in B, which means that there would be no intersection between A and B complement, all right? So, since I think it's true, I need to prove it. So, our proof, I think this one we'll do by contradiction. All right, so let's set it up. We'll let A and B be any sets such that A is a subset of B. Okay? So now we're going to suppose the negation of that conclusion after the then statement, right? So here, suppose there exists some X such that X is an element of A intersect B complement. So do you see how that contradicts this statement? That's right here. Cool, cool? All right. So here, all right, by definition of intersection, so we're doing this using elements, what do we know? X would have to belong to A, and X would have to belong to B complement. Cool so far? But A is a subset of B. So X would have to belong to B, and X would have to belong to B complement, which is impossible, right? So we'll just say it's a contradiction. Cool, cool. So we've proven what we needed to prove. Alrighty, what about this next one? For all sets A and B, if A intersect B is the empty set, then the Cartesian product of A and B is equal to the empty set. Well, I don't think this one is true, because when you're dealing with the Cartesian product, you don't have to have an intersection for the Cartesian product to work. So let's check it out. I think this is false. So our counterexample is going to be, let's just make it real easy. Let's let A equal to the set that contains the element 1, and B equal to the set that contains element 2. So original. So A intersect B is equal to the empty set, which it needed to be, all right, because that's in part of our premise. But the Cartesian product of A and B is equal to the set containing the order pair 1, 2, right? So make sure you know your definitions, and that, of course, is not equal to the empty set. So we've shown that this is a false statement by finding a counterexample. All right, so next up, we are going to look at algebraic proofs for sets, okay? So in your homework, it has you cite the properties, and I think it was in 6.2. I'm just going to use the names for this. I think it's more illuminating. So anyway, we'll just go through and check it out. And if you want to, have a visual with you, you can look at your book and follow along and have it open to the properties from 6.2. Theorem 6.2.2. All right, so here we go. For all sets A and B, the difference between A and B union, A intersect B, is equal to A. All right, so here we go. We're going to let A and B be any sets. So let's work with the left-hand side. And these can get a little tricky. If they're getting too long, it might mean that you missed maybe some sort of absorption property or identity property that you could use. Okay, so here I'm seeing this difference deal, and a lot of times, if we rewrite that as the intersection, that might be something that will get rid of some stuff for us. So here we go. The difference between the sets A and B is equivalent, remember, to A and B complement, right? So A and not B. And that's still unioned with the intersection of A and B. And so what we used here was the set difference. And they're all laws or properties. So I'm just going to say set difference. Okay, and then now that we have that one going on, let's see what we have. This will be equivalent to, so here I've got, something that I can use the distributive laws on. So I'm going to treat this here as a, single entity and distribute it to the other one. So we will have A intersect B complement union A and then intersect, so the union was from here, and then the intersect will be from the second one here. So intersect A intersect B complement union B. So again, this intersect came from the green one, and then this union, the second union, came from us utilizing that distributive property. So I'm just going to put DIST. And then next up we have, well, here you have to go in the same order. Okay, as you've seen, you can't, like what I'm saying is you might know that this here is just going to be A, but you have to use the commutative property to get it in the right format as it is in the theorem list. So this is equivalent to A union quantity A intersect B complement. And then I'm going to do the same thing over here. We will have B union A intersect B complement, that whole quantity. And that both of those were by the commutative laws. Now be careful here. This is actually an absorption law. All right. If you have, A union A with some intersection of some other set, you're going to end up just getting A. Okay. So basically right here, this one here is equivalent to A. And then we'll be intersecting this one with using the distributive property to get B union A intersect B union B complement. So we used two different properties there. The one that we did in pink was from the absorption. And then the other one was the distributive laws. Okay, so next up, what do we have? Well, all right, so now we'll have A intersect. I'm going to go ahead and commute the A and the B in this union here. And then it's going to be intersected with what? Beautiful, that universal set, right? Because B union B complement is the universal set. And that is under a complement property or law. So here we go. This one was from our commutative and complement laws. All right, so continuing. Any set which is intersected with the universal set is that set itself. So we'll have A intersect. So now let's commute the universal set and the set A union B. So that's the commutative law. And then now we can use the distributive law, right, to get the universal set intersect A union the universal set intersect B. Distributive laws. And then what's going to happen? This will be A intersect. Okay, so here when we do the intersection of the universal set and A, we're going to get A, and then the intersection of the universal and B will be B. Good so far? And those come out under the identity laws. And next we have A intersect A union B is an absorption law, and that is just A. And that is the right-hand side. So we're all done with that proof. Cool? All right, so next up, number 2, again, we've got our set difference. So let's kind of go through. And if you feel confident, just go ahead and try doing these yourself. They're kind of fun. So remember, if it ends up being kind of circular, you probably forgot either an absorption law or an identity law or something like that, or an idempotent law that comes into play too. Cool? All right, so let A, B, and C be any sets and actually, we should probably say add which are subsets of a universal set U. I should probably add that to here. Since there's a U in there. All right, so for our left-hand side, because that's the most busy, we have the difference between A and B minus the difference between B and C. And we want to show that that's equal to the difference between A and B. So let's check it out. This will end up being what? I'm going to take care of, this overall difference first, right? The difference between these two sets. And then we'll go and start working within. So this is going to be equivalent to the difference between A and B and not the difference between B and C, or the difference between B and C complement. Good so far? So that is by set difference laws. And then in turn, we will get what? What do you think we should do? Good. I think we should use set difference laws on each one of them now. So the difference between A and B is equivalent to A and not B, or A and B complement. And then intersect B and C complement, and then the whole thing complement. And so again, we have set difference laws. So we use that 3 times. And now let's see what we've got. Let's take care of the complement using De Morgan's laws. So we'll leave this A intersect B complement alone, and that'll be intersected with B complement or C complement complement. And that was one of our De Morgan's laws. And then we have A intersect B complement intersect, B complement union, good, C, and that was by the double complement. Law. Alrighty, continuing. Now we're going to distribute. So this will be A intersect B complement, intersect B complement, union A intersect B complement, intersect C. Now, those were distributive laws. And then let's see what we've got. So notice that they're all the same symbol, right? So when that happens within the parentheses. So when that happens, we might want to look at using the associative property. So here is, this would be equivalent to A intersect the quantity B complement intersect B complement, and then union, let's see on that one, I think I'll just leave that one alone. It's not really going to help me to change this one up, I don't think. Not at this time. So this one, Associative Laws, and this in turn will give us B complement intersect B complement ends up just being B complement, and that's one of the idempotent laws. So we'll get A intersect B complement, and that B complement comes from this part here. And then that'll be unioned with A intersect B complement intersects C. And that was by idempotent laws. And then, next up, what do you think we should do? Be careful. I got to tell you, I was very tempted to distribute the A intersect B complement through that second quantity. But if you look at that one, we can use the absorption, one of the absorption laws. You've got this guy, and it's unioned with an intersection that includes that set A intersect B complement. So this is just A intersect B complement, and that's from an absorption laws. But what is A intersect B complement but the difference between A and B? And we're back to set difference laws. And that's our right-hand side. So we're all done. Cool, cool? All right, so next up, we've got this one here. And this one I think is actually our last problem. Yep. So here we go. For all sets A and B, the difference between A and B union A intersect B is equal to A. So for our proof, we'll start off the same. Let A and B be any sets which are subsets of a universal set U. So our left-hand side, again, is the busiest. So the difference between A and B union A intersect B, let's see what we get. Well, again, I like changing up the difference between sets into an intersection. So this is going to be A and B complement union A and B, and that is by set difference laws. And then let's see what we'll do now. So let's go ahead and distribute. So we'll have A intersect B complement union A intersect A intersect B complement union B. And those are our distributive laws. This will in turn give us what? Good. We need to commute the A and the A intersect B complement, and keep your eyes open. That's going to be one of the absorption laws, and that's intersected with. We'll switch this one around to be B union A intersect B complement. So we just use commutative laws here. And then continuing, this one here is just A, right? And that one is by what? An absorption property, right? And then what should we continue with? Well, we've got this intersection going on, and why don't we go ahead and distribute the B? So we'll have B union A intersect B union B complement. So we used absorption and distributive laws. Cool, cool? All right, and then now we'll have A intersect I'm just going to commute the A and the B here. And then B union B complement is equal to the universal set by complement laws. So we used, let's see, what all did we use? We used commutative and complement laws. And then that's going to give us A intersect. Good. A union B, and that's by using what? Good. This was from one of the identity laws. And then now, and that was that we get this guy is equal to this. And so now we have, using our absorption laws, we get just A. And we're done because that's equal to the right-hand side. Cool, cool. And that's it for today. So I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, please subscribe and tell your friends. Bye.